And with this, Zoyan, we are very excited to hear from you, and the stage is yours.
So, test. Thank you so much. So this talk is about the theory of language models. But the word theory, can mean lots of different things in different people's mind. In the community where I came from TCS, like theory of computations, in which by theory we actually mean prove mathematical theorems, in which we define concept classes, we make assumptions on the data, on the model, and then we try to prove learnability theorems. So that's what we meant by theory. But the word theory actually means a lot of things, a full spectrum of things. On the other extreme, it can also mean like ethology or animal behavior science. Whenever you subscribe to OpenAI's API, then you can play with GPT-4 or GPT-4 Mini and try to get very interesting results over there. For instance, the very celebrated chain of thought was obtained in this way, and this is also theory of language models. So in these two extremes, there are definitely pros and cons. So let's begin with the pros. So on the mathematical side, we love it because we can prove rigorous theorems. And there are also a lot of pros on the ethology side. That is, everyone can do theory. You can play with super large language models, and the results, don't get me wrong, the results can be very educational, right? Not only chain of thought, tree of thought, and many interesting concepts can be derived out of this type of theory. But there are also cons. So the cons on the mathematical side is that the assumptions you make are typically too idealistic, and the networks you can prove are typically very shallow, like maybe a one-layer transformer. And only in very rare cases, the theorems that you prove really do connect to practice. And even if it does, people may not read your paper because it's too long. So the actual final deal breaker, actually, for me to step out of that community was because to make progress is very slow over there. So nowadays, in academia, we have NSF grants that are maybe between 3 and 5 years. But in industry, where I currently work for Meta, for Fair Labs, we make plans that are maybe in 6 months and so on. So this actually makes some sense because if you think about it, 2 years ago, we didn't even have ChatGPT. And 1 year ago, we didn't even have the intelligence at today's level. So if by proving mathematical theorems, you're making very slow progress, then how could you make sure the theorem you're proving maybe a year later, it still apply, right? So let me actually remind everyone that the humankind used to be very, very patient. So in the old days, when Isaac Newton actually developed the laws of motions and gravity, as well as calculus, that was in the year of 1687. And how did Newton achieve this? So there is the story about the apple tree, right? But that was only the beginning. That was the thing that drove Isaac Newton into the field. But in fact, the entire theory from Isaac Newton was built upon Johannes Kepler's 3 laws of the planetary motion. That is the eclipse and the Fourier laws. And guess what year was it? That was between 70 and 80 years before Isaac Newton. So this probably most of you have heard about. But a very less known fun fact about this whole history that most of the younger generation did not know is that Johannes Kepler was actually an assistant to this Danish astronomer, Tycho Brahe. And Tycho Brahe was the head of the observatory, and he actually spent an entire 20 years to collect observatory data. And that was even 30 more years before Kepler. And Kepler was the assistant to this observatory, and after the death of Tycho, Kepler inherited all of those experimental data. And that was the thing that actually Johannes Kepler built his 3 laws of planetary motion, and that was the entire start of this Newton's law of motions and gravity. So if you count everything together, that's more than a century ago, right? So the humankind used to be very patient. Not anymore. At this point, maybe you're thinking that, am I trying to make the following analogy, that is maybe Newton's laws is more like proving mathematical theorems about language models, and maybe the Tycho's observatory data is more like ethology, is more like playing with GPT-4. But in fact, even this is not what I meant. I think there is still a gap between ethology and physics. That is, if you just play with large language models to try to make educational guesses, then there are a lot of concerns. So concern number one is that studying models that are pre-trained using internet data may not be scientific enough. So for instance, like nowadays, it's very easy to to observe bugs of GPT-4 or maybe Llama 3 and so on. So people are now talking about the 9.9 versus 9.11, but my favorite bugs was actually the ones we discovered at the end of last year. That is, you can ask GPT-4 to do parity checks on, for instance, what's Joe Biden like born in an odd year or even year. Or like you can ask GPT-4 to, for instance, compile the birthdays of two celebrities like Donald Trump versus Nancy Pelosi. And it's actually going to like produce errors almost all the times. And then, the chance that he gives correct answer is like flipping a random coin. So in order to study really scientifically like what is happening behind the scene, I believe that it really requires us to do very careful controlled studies to see why exactly this happens. So could it be because the knowledge is not properly stored in the model, or could it be because maybe the parity test is too hard, maybe the model doesn't know what even or odd means, or could it be something else? So actually, as we will see, the reason is because of something else. Okay, so therefore, like, we need full control of the data. If you only play with a pre-trained model, it's very hard for you to make scientific discoveries about what's exactly happening. Another concern I want to point out is that just by studying individual models, this may not be scientific enough either. For instance, this means we have bugs for GPT-4, but that only apply to the July version of GPT-4 of this year. Does it apply to the August version or maybe the version of next year, right? So ideally speaking, we want to identify big issues with language models, not only like to a specific version of a language model, but we want to develop like general universal principles that can apply to all the possible language models. So this is the hope. We hope the statements can be regardless of how you pre-train or how you fine-tune and so on. A third concern is that people are nowadays like talking about data contaminations. So we can no longer maybe rely on benchmarks. Maybe very celebrated example is the GSM-8K dataset, which only has 8K number of math problems. So if a model is like very good at solving those 8K problems, could it be because of data contamination? Right? I'm pretty sure that nobody will intentionally cheat to put this data into your pre-trained data. But what if, imagine, like tomorrow, I translate all of the problems into French, into German, into like Chinese. I put it on my MIT website. Because like MIT websites are very likely to be crawled by the language models, then could it be that from tomorrow onwards, then all of the models will be cheating just because of this action? By the way, I haven't done this, but if I do this, imagine, right, then it's no longer a trustable benchmark. The fourth concern here is that I think the biggest concern is that just by playing with those monkeys, you really see nothing about the internals of how those language models work. And if things work, then how do they work? And if things fail, then why do things fail? So we want to study this like more scientifically. So to this extent, I think like ethology, or the idea of just playing with GPT-4, is more like maybe geocentrism in BC 400 to 200. That is like just by watching maybe two models, like a sun and a moon, like going up and down every day. You can form theories, but maybe the theory you can create may not be really like to be the most comprehensive and the most real theory behind the scene. So to this extent, we really put forward this initiative that we call the physics of language models. That is, we are emphasizing on 4 different things. Number one, we really wish to decompose the idea, the concept of intelligence into building blocks, and then to study them one by one, like language structures or knowledge or reasoning and so on. Let's study them like one by one. Do not mix everything together. That would be like too complex. And 2, let us build synthetic data to study everything in a controlled setting, in an idealized environment, so that you can tweak like the data's difficulty, the data's type, the amount of data, or the data's formats, and to see like how those individual things affect the model's performance. And in this way, like you can start to make very informed knowledge about like what you should do in when like if you're going to train like tomorrow's next generation of language models. The third thing we're advocating is to really make the experiments highly repeatable. So if pre-training a model costs like $10 million US, then that would be too expensive. You cannot afford doing like repeated experiments. If you have like say 7 different things you want to try, you cannot afford like turning each of them up and down to do controlled experiments to figure out what exactly is causing like the final outcome. So therefore, like we really propose to study smaller models of maybe models of only 100 million parameter sizes. And as you will see throughout today's talk, just by studying those smaller models, you can also make very universal, you can also like derive very universal laws about language models. The reason here is because we are not focusing on the entire concept of intelligence altogether. We're focusing on just individual building blocks. And also we are building synthetic data, so we are in a very idealized setting. In this setting, you do not need a model size to be super huge. And finally, like we're really advocating for doing probing, that is to see the inner workings of language models. So here is the structure of today's talk. I'm going to cover 3 main parts, respectively regarding the, how language models learn language structures, reasoning, as well as knowledge. So I'm going in actually the reverse direction. That is, I will start with part 3, that's about knowledge. So this part is the joint work with Professor Yuanzhi Li from Mohammed bin Zayed University of Artificial Intelligence, MBZUAI. So I will begin with this counterexample I showed you a few slides ago. That is, large language models just generally fail on, for instance, doing the parity test for the person's birth years, or maybe comparing the 2 celebrities' birth dates. And you can actually keep getting counterexamples like this very easily. Now, how to study this type of counterexamples, right? You can, of course, test it upon like a model to see like how accurately it performs. But I claim that before you even attempt to do this, there is a prerequisite that you need to keep in mind. That is, if the model fails on such a problem, then could it be because the model cannot extract the birth year of celebrities? Or maybe more specifically, for instance, could it be because the model did not see, for instance, Joe Biden's biography in its pre-trained data? Or maybe if the model has seen such biography, could it be because the model cannot extract the birthday information of celebrities? Or could it be because maybe the model can extract the birthday about certain celebrities, but not other celebrities? So in fact, we spent an entire paper to study under what conditions language model can extract knowledge that he has seen in the pre-trained data. So this itself is already an area that deserves performing some controlled experiments. So this we will see first. So once we are certain that the model is capable of, for instance, extracting the birth dates of every single celebrity on Wikipedia, for instance, now we can start to test the model's performance on manipulating knowledge, such as performing knowledge classification, like the parity test. Is it even or odd? But I claim, even here, there are still a lot of subtleties. So if the model successfully answers the question of if Joe Biden was born in an even year, could this be because of data contamination? So this, for instance, was a counterexample we discovered at the end of last year. If today the model succeeds on this specific question, could it be because we have put the paper on archive and therefore this question got revealed to the newer generations of the language models? So we need to exclude the possibility of this in order to study this question properly. And similarly, if the model fails to answer this question, could it be because the model just does not know what even or odd means? Maybe it did not get fine-tuned enough to do the parity test properly. So therefore, to study the language model's true capability of manipulating knowledge, you have to also get rid of the scenarios B and D. So you have to do very careful controlled experiments. So this is actually what I will cover in part 3.2. So I will begin with 3.1, that is, under what conditions language models can extract knowledge. So I'm going to divide it into some sub-results. To study this properly, as I mentioned, I need to design a knowledge data set. I need to design some synthetic data set. What is the knowledge that comes to your mind that's the most natural one? So to me, like it's biography, right? People's biography is some sort of knowledge. And indeed, we build synthetic biography data of fake random people. And we either use maybe a set of sentence templates before we generate the biographies, or we use some LLMs to actually help us to generate the biographies. And for now, imagine that we have n individuals, and we generate one biography entry per person. So this is the biography data that we create as a synthetic data. And at the same time, we also prepared QAs. This is like instruction fine-tune data. That is, each person has 6 attributes: the birth date, the birth city, and the university, the major, and the employer, and the work city. So then we prepare 1 question for each, 6 questions for each person, corresponding to the 6 attributes of the person. So these are the QA data. And here is the experiment setup. That is, we only reveal half of the QA data to the training, and then evaluate the model out of the distribution on the remaining half of the individuals. So in this way, we can do a controlled experiment by separating out really the training set from the test set. And if the model is capable of getting high accuracy on the test set, then we say this is the skill of knowledge extraction. So if the model is capable of extracting knowledge for this half of the people in the training set, that's not knowledge extraction, that's only memorization. But if it can generalize the skill of the QAs onto the other half of the individuals based on their biography data, then we say this is knowledge extraction. Okay, this is how we define knowledge extraction. And now comes the first result. That is, suppose you do mixed training. That is, you put both the biography data and the QA data into the training, into the pre-training process. And then, out of distribution tested on the remaining half, the accuracy is high. In short, if you do mixed training, you get knowledge extraction to a very good accuracy. But this is not what people do in practice. Maybe you should, but this is not what people do in practice. In practice, people do this. That is, they first pre-train the data on, for instance, Wikipedia and so on, and then they instruct fine-tune the model, and finally reveal the model to the users to out-of-distribution evaluate it. So if you follow this procedure, and even if like you perfectly pre-train and say close to perfectly like instruct fine-tune, then we discover that the model will perform just very bad on extracting knowledge. So this is actually a universal statement. It's independent of how large the model is, which architecture you use. You can use like GPT or GPT-2 or Llama, Mistral, and so on. It's independent of the data size. You can try different data sizes. It's also independent of the training parameters or fine-tuning parameters. You can use LoRa of different ranks. And in all of the cases, we actually tried more than, I think, 500 possibilities here. All of them give you like a 0% accuracy, close to 0% accuracy. So this was really mind-blowing the first moment I did this experiment, until I realized one catch. That is, here, we're only having 1 biography per person. What if you have more biographies? This is what we call knowledge augmentation. So suppose you augment the pre-trained data to make sure that the knowledge is not described only once, but described multiple times using different writing styles. Maybe the sentences are permuted, maybe like you change, you do translation from English to French, or maybe you just rewrite the biography of each person, say using some small model. Then the accuracy suddenly increases. So for instance, if you have 5 biography entries per person using different writing styles, you get 96% test accuracy. So to summarize, unless you do mixed training, but if you don't, it's absolutely necessary for you to knowledge augment the pre-trained data before the knowledge can become extractable. Okay, so in this controlled setting, we actually discovered this. But why did this happen, right? The main theme of today's tutorial is not only to discover phenomena, but also to discuss why. So we did probing. we use probing techniques to actually exactly study like where and how knowledge is stored inside a language model. So for instance, if you pre-train a language model like GPT-2 in this biography data, and now let's try to do probing by feeding a biography entry as the input to the transformer. So now it's already pre-trained, we feed the input once again to the model, and we look at the hidden states of the last layer. Okay? So now we try to do probing to see, like, from those probing positions, how much knowledge of this person's biography is stored in those like probing positions. So let's take one example. Suppose we care about the knowledge about this person's employer name, in this case, Meta Platforms. Then if you probe from position 4, of course, like that position's hidden state should encode like what is this person's employer name, because the training task is autoregressive, right? It's about predicting the next token. So therefore, the hidden states at this point definitely should encode at least the token of Meta, and therefore, like very likely, like Meta Platforms. So what we are more interested is from those previous token positions, does the hidden states actually also encode the knowledge of this person? So the answer is very striking. That is, if you do not do knowledge augmentation, then from all of the previous token positions, the probing accuracy is very close to 0. But if you do knowledge augmentation, that is, once you have multiple different writing styles, the model stores knowledge in a very different way by making sure that, by satisfying that at right after the person's name, then already from here, if you do probing, then this hidden states already stores the knowledge about this person's employer name. So let me elaborate on this. That is, if you do not do knowledge augmentation for the pre-trained data, then the model tends to learn the wrong logic. It may not learn like it was Anya who works for Meta Platform. It may learn the wrong logic. That is, it's someone who was born like on October the 2nd, 1996 in Princeton, New Jersey, who studied communications at MIT, works for Meta. Or in the mathematical form, it could happen that the knowledge of value 5 is jointly stored in this tuple, which is defined by the key as well as all of the values before this. But if you do knowledge augmentation, because the values can be, for instance, permuted, it may not be always in the same order, in this way that the model tends to store knowledge in the right format. That is, it is Anya who works for Meta. Or in the mathematical form, like value 5 will be directly stored onto the key. In this case, it's the person's name. So this is what happened behind the scene. To summarize, we discovered that if you pre-train a language model with knowledge augmentation, this changes the behavior of how knowledge gets stored inside the language model. And this, in turn, affects whether or not the knowledge can be further extracted via instruction fine-tune. So this is like what you can discover if you do controlled experiments. So now we know that it's important to augment knowledge, but what's the fraction of the knowledge do we have to augment? Do we have to augment everybody? It turns out you don't. So let's consider the following controlled experiment. That is, you have maybe some celebrities and some minorities. For the celebrities, their biographies are very rich, so that on the internet, for instance, you see at least 5 biographies of the same person written in different writing styles. But there are also minorities. In each of them, you say you only have 1 biography entry for each minority. So in this case, suppose you pre-train the 2 kinds of data altogether, and now also fine-tune the model with respect to the QAs on the celebrities. So now, first of all, we definitely know that the model out of distribution generalized to the rest of the celebrities. But what's more interesting here is how does this affect the knowledge extraction for the minorities? It turns out the accuracy is pretty high. So let's take a moment to appreciate why this is significant, because for the minorities, their biographies have no knowledge augmentation. And on top of that, the minorities did not even appear in the instruction fine-tune data. Yet, the mere inclusion of the celebrity data in the pre-training actually enhances the model's knowledge extraction for the minorities. The reason behind this, actually, we also did probing, is that the mal-inclusion of the celebrity data actually teaches the model to store knowledge in the right format. And that causes the model to also perform well on the minorities. So we actually call this celebrity helps minorities. So for instance, like Donald Trump's biographies have been appearing so many times on the internet. And the mal-existence of those biography data actually helped all of the language models' capability on extracting knowledge about biographies for the minorities. So to this extent, Donald Trump actually helped minorities, although maybe he did not intentionally do this. Okay, but I have a mathematical proof this actually happened. All right, so we call this, so as a result, it's really sufficient for you to augment only part of the people, and that will give you knowledge extraction for all of the people. So to summarize on this part 3.1, I showed you that there is a distinction between knowledge storage versus knowledge extraction. That is, even if a model can 100% word by word memorize knowledge, such as biographies, it does not mean that the knowledge can be always extractable. And how to make sure knowledge is extractable, you either do mixed training, or if you don't, then you had better make sure the knowledge is augmented. So the last result, which I didn't show you today, is that if you use bidirectional models, like BERT or DBERDA, so all of them will fail. They do not give you knowledge extraction, even if you do mixed training together with knowledge augmentation. So for language modeling, for GPT, if you do one of the two, you get knowledge extraction. But for bidirectional models, even if you do both of them, you don't. So the explanation is in the paper. You will see that. So that concludes part 3.1. Let me now jump to 3.2 about knowledge manipulation. So for this part, I'm going to assume that the knowledge is already fully extractable. And then I want to study further the skills of language models regarding how much they can manipulate knowledge. And there are a lot of different ways to manipulate knowledge. The simplest possible task I can imagine is knowledge classification, such as the following. That is, suppose you have a model that you, once again, pre-train on the biographies, and then you fine-tune it to make sure that all of the birth dates of everybody can be extractable. So this, suppose you have already done this, either using maybe mixed training or maybe using knowledge augmentation. So from the previous part, we see that you can do that. But now comes the interesting thing. That is, let's try to study the task of knowledge classification. And maybe the simplest possible classification task is regarding classifying 12 months into even or odd, into two categories. Okay, classifying 12 months into two categories, yes or no. So this is the simplest possible knowledge manipulation task. And here, we not only consider the knowledge classification without COT, we also consider the version of that with chain of thought, with COT. That is, the model first spells out explicitly the birth month of this person, and then followed by yes or no. So we consider both kinds of data. And now suppose you do this fine-tuning sufficient enough to get the perfect accuracy, then let's once again evaluate the model's classification accuracy on the remaining half of the individuals. So we found something very striking. That is, if you do this procedure, the accuracies for the out-of-distribution people, for the remaining half of them, is extremely low if you do not use COT. In other words, we discovered that knowledge manipulation, even in the simplest one step of the most basic kind of knowledge manipulation task, in this case is knowledge classification, but you can also try others, you can also try ranking or comparisons. For all of them, if you do not use COT, then the performance is just like random guess. So in fact, what is even worse here is that the inclusion of COT in your training does not help the accuracy during evaluation without COT. So this means you both need to include the COT in your training data, as well as when you're deploying the model, you have to encourage the model use chain of thought. That is to explicitly spell out a knowledge before it can manipulate knowledge. So this COT is very different from COT in reasoning, which I will cover actually later in today's talk. That is, you can imagine GPT-4 is very capable of, for instance, answering is the sum of two numbers even or odd without actually writing down the sum A plus B explicitly. For instance, for A and B, like between 1 and 12. So you can do this very easily. So you can skip steps. But for knowledge tasks, for knowledge manipulations, it cannot. It always has to write down the explicit knowledge before it can do any simple operations on the knowledge. So this is a very strong statement. And in fact, it's a statement that you can only derive it if you do controlled experiments. So that's about knowledge manipulation, such as like classification or comparison and ranking and so on. Another manipulation task we studied was inverse search. That is, let's try to fine-tune the model to answer like who was born on this date in this city and works for blah, blah, blah. And the answer is Anya, like in this case. And let's, again, to test this out of distribution on the remaining half of the individuals. And here's what we discovered. 0 accuracy. So our conclusion here is that knowledge inverse search is literally just impossible, period. So this is, once again, a universal law. So I'm stating this regardless of the model size, regardless of the data size, regardless of the training method. You can use like mixed training or fine-tuning, whichever you like. You can like fully augment your data by like asking like GPT to like rewrite your data several times, and you can also change your fine-tuning method and so on. In all of them, so I'm writing a single number 0 here, but what's actually hiding behind the scene is once again like hundreds of different types of pre-training that we tried, and in all of them, it just fails. So unless really the pre-trained data is already knowledge reversed, only in that way, for instance, if you put the person's name at the very end of every single biography, only in that case, you can do inverse knowledge search. So we actually, with my colleagues from Meta, we actually wrote a separate paper regarding how to practically, very easily to reverse knowledge. But the key point here is that if you do if you reverse knowledge in the fine-tune stage, that would be too late. You really have to reverse knowledge in the pre-train stage. And also, you cannot hope for like changing from, say, unidirectional models like GPT to bidirectional models like BERT. If you do that, it also doesn't solve this issue. Okay, so that's some negative examples regarding language models' knowledge manipulation capabilities. And let's also connect this to practice. That is, we also tested the same thing on GPT-4 or Llama and realized that, for instance, if you try to ask GPT-4 or Llama, like, was Joe Biden like born in an even year or odd year, then you can try it with all of the celebrities on Wikipedia, then the answer is just pretty like flipping a random coin. So large language models also fail on this. You can also try like ranking, for instance, comparing to celebrities, and you can also realize that large language models, if you compare celebrities that are like, say, born like within 10 years to each other, then the accuracy is also similar to flipping a random coin if you do not use COT. But if you use COT, then the accuracy will greatly improve. So therefore, like what we discovered using controlled experiments on smaller size models actually do apply in practice for very large models. So another thing we tested is inverse search. You can design different types of inverse search. But to me, like my favorite task was actually this Chinese idiom task. So in Chinese, we have these Chinese idioms, which are like 4-letter idioms that we really use in our daily conversations. So you can mask out, for instance, the first letter out of a Chinese idiom, and then ask like GPT-4, like, what is the missing letter? So I can tell you very confidently, at least for 1/3 of the Chinese speakers in mainland China, we are able to answer this question like very accurately, but not for GPT-4. So therefore, like this is another evidence that the large language models today just cannot do inverse knowledge search. So once again, this is ethology. It's not what I really want to do. So in order to really state something like something strong, you have to do like controlled experiments that, for instance, can tell you that these bugs just cannot be easily fixed. So for instance, we discovered those bugs like last year in September, but still like you can see these bugs like showing up everywhere, like in every single language model of today. On the other hand, actually, this also gives you a Turing test that can distinguish all of the modern AI models from humans. Because if you ask, for instance, who was born earlier, like for your mom and dad, you don't need to explicitly like say what's their birthday, but you can directly say yes or no. Right? You can directly do the comparison, or maybe saying out somebody's birth year, is it even or odd? You don't need to say the year out loud. You can do this mental calculation, but large language models cannot. Okay. So this actually pretty much summarizes part 3.2. I'm actually skipping one result, that is knowledge partial search. So we discovered that language models, although they can fully extract the knowledge, for instance, the birthday of a person, but it may not be able to extract, for instance, the last word of this knowledge, which is the birth year. So the accuracy of these two can also be very different. So this is actually related to this paper from my colleagues in Meta. That is, they proposed this idea of multi-token prediction. So if instead of like predicting only the next token, you ask the model to predict multiple future tokens, so this will actually change how the knowledge is stored in a language model, and it may improve its capabilities. So this is actually a result I'm skipping today. The result I covered is that a language model just cannot say birth year is even without saying the year explicitly. So this is really needed. Once again, this has nothing to do with the COT for reasoning, which will come later. And I also told you that knowledge inverse search is just literally impossible unless you already like reverse the order of the knowledge in your pretrained data. And finally, and by the way, there is a concurrent work to us that actually give a name to this phenomenon. They call it reversal curse. That maybe many of you already heard about it. You know, they summarized it already in the paper title. That is, if you train a model on A is B, then the model cannot learn B is A. So that's the same thing we discovered here. So finally, I also showed you some connections to practice. So this summarizes 3.2. So in the next part, I'm going to tell you scaling laws regarding knowledge capacities. Okay, so the first result I'm going to tell you is regarding all language models can store knowledge in this ratio that is 2 bits per parameter. Okay, so before I do that, I need to define what do I mean by bit. So I mean actually information theoretically, the number of bits in your data. So how to measure this? With the help from synthetic data, if you randomly generate a synthetic knowledge data, then you can actually measure how many information bits are there in your data set. So for instance, if Anya's birthday is randomly generated, say uniformly at random, from like 12 months and 28 days and 200 years, then this is log 2 of 12 times 28 times 200 is like 60.21 bits of knowledge. And similarly, like if Eugil's birth city is Washington, D.C., and if this is randomly generated from 300 different cities, then this is 8.23 bits of knowledge. So therefore, like if you design a biography data with n people and with like say 6 attributes that are generated according to a certain distribution, then you can compute exactly how much amount of information is like representing this data set. And this is, by the way, regardless of the writing styles. You can, for instance, like rewrite the biography of a same person like 40 different times, but it's capturing the same knowledge. So therefore, the amount of knowledge in terms of information theoretic bits is not changed. So another way to do the synthetic data is to create like more parameters that is, instead of thinking about people biographies, let's make it more general. So for instance, we can study knowledge that has like a vocabulary size T and maybe some diversity D and so on. So you don't need to read all the parameters. The point here is that for any type of synthetic knowledge, you can actually create a formula to actually compute what is the amount of knowledge bits stored in this data set. And now suppose you pre-train a language model on a knowledge data that is synthetically generated like this. You can start to compute how much knowledge is stored in this learned language model. By the way, this is not trivial. So if the model achieves 0 loss on this data set, then of course it has fully captured the knowledge. But what if the model is only, say, half correct kind of on this data set? Then you have to be a little bit careful to compute what is the discount factor in front of everything. That is, what's the exact amount of knowledge the model has learned. So if you do that, then you can start to draw scaling laws. So this is a more scientific version of the scaling laws comparing to what you have previously seen. And our major discovery here is that LLMs, like all LLMs, they can consistently achieve 2 bits per parameter in terms of storing knowledge if the data is being sufficiently trained. Okay, so I'm going to define what's sufficiently trained on the next slide, but here, let me first explain what do I mean by universal. So here I really mean that for a wide range of model sizes, depth and width, as long as you study transformers of 2 layers, only size matters. And the 2 is that this is regardless of data types. You can use any of the data of this form. You can vary like the different parameters of the knowledge data, but it's always the same. It's always like 2 bits per parameter, and regardless of how you rewrite the data and so on. And also for a wide range of the parameters, this just universally holds. So from here, actually, we made a conjecture. That is, in the paper, we actually computed, we actually estimated how much amount of knowledge are there of humankind, especially for all the English Wikipedia plus all the English textbooks. So we actually estimated how much information bits that are there. So we predict actually a 7 billion sized language model should be sufficient in terms of storing all of such knowledge. So of course, we haven't reached there yet. But I'm claiming that this should be what we are shooting for. So this is definitely very plausible. And then maybe like in 2 years, if we haven't reached there, then we need to rethink, are we doing something wrong? So now let me explain like what do I mean by sufficient trained. That is, I claim if all the knowledge got exposed to during the pre-training, if each piece of knowledge get exposed for 1,000 times, then we can reach this 2 bits per parameter capacity. So here is what do I mean by exposure. I do not mean like the training data is trained for 1,000 passes. So I mean that each piece of knowledge is seen for like 1,000 times. So for instance, the knowledge about the US capital being Washington, DC may have been exposed maybe 1 million times if you just do one pass of the internet pre-trained data. So therefore, by exposure, I just mean the same knowledge. Then it may have been like exposed multiple times, but using different writing styles. But I count that as multiple exposures. And let's do the controlled experiment. That is, suppose each piece of knowledge is exposed for the same number of times. All of them say 1,000 times. Then we achieve this 2 bits per parameter scaling law. So the correct way to read this picture is that if you fix the data size, then when you increase the model, you cannot learn more knowledge, because you only have this much of knowledge in the data, right? But the interesting thing is that before you reach that point, the model's capacities in terms of how much knowledge it has learned actually closely follow this 2 bits per parameter line. So this is how we derive this 2 bits per parameter scaling law. And by the way, this picture currently is for GPT-2, the rotary version of that. And actually, it doesn't matter how you change the architecture as long as you use the mainstream architectures like Llama or Mistral. And even if you remove all of the MLP layers, you only have attention layers, you still hit this 2 bits per parameter line. Okay? But in contrast, if you do insufficient training, that is, suppose the knowledge is not exposed too many times, say that each piece of knowledge is exposed only for 100 times, or equivalently speaking, those are about rare knowledge, so they do not appear enough number of times on the internet. So for those kinds of knowledge, the knowledge capacity actually decreases. It decreases to 1 bit per parameter, more or less. And here, the more interesting thing is that if you focus now on such rare knowledge, or equivalently insufficient training, then there starts to be a difference between model architectures. If you use GPT-2, that's good, but if you use Llama or Mistral, it becomes bad. And actually, you have a factor of 1.3 difference between using GPT-2 versus using Llama. So the performance will actually get worse if you use Llama Mistra. I'm going to explain why this happens, but before that, let me also tell you that even if you reduce the size of the MLP layers of GPT-2 by a factor of 4 to make it actually smaller than the attention layer, still you do not have any capacity loss. But if you completely remove the MLP layers, then in this scenario, you're going to have capacity loss. So 2 disclaimers. So number 1 is that this comparison is only for knowledge capacity. Okay, it's not about like other things like reasoning and so on. And disclaimer number 2 is that it's for rare knowledge. So if you consider like the knowledge that appear frequently on the internet, for instance, with 1,000 exposures, I told you that there's no difference across model architectures. But here, for the rare knowledge, there is a difference. So this is one of the good things about doing controlled experiments. So you can exactly figure out for what type of data, for what kind of tasks, maybe one model is better than another one. So you can do more controlled experiments to compare model architectures. So here, actually, we exactly pinpoint to what caused Llama or Mistra to have a poor performance. That's because of the gated MLP. So if you compare the difference between GPT-2, the rotary version of that, versus Llama, there are actually 7 total differences, like different activation functions, like Silu versus Galu, or maybe different layer norms. But in the end of the day, you can try to turn on and off like each of them, and you can figure out it's the MLP layer. That is, if you take Llama and replace its gated MLP with vanilla standard MLP, then the knowledge capacity just improves back to the original 1 bit per parameter. So it improves by 30%. So this is like one of the good things about doing controlled experiments. So the last thing I want to show you for part 3 is that we also did a controlled experiment regarding data that has mixed qualities. So let's imagine that we not only have data that is rich in knowledge, such as like the Wikipedia, but we also have data that are not so good in knowledge, such as the Common Cross or internet junks. So let's now compare 2 scenarios. In scenario 1, you train your model only with respect to good data, the data that is rich in knowledge, and suppose like you make sure each piece of data is exposed exactly 100 times during the pre-train. And in the other scenario, you train both with the good data and with the bad data. But you still make sure that each piece of good data is exposed 100 times. You make sure it's a fair comparison. And now you can start to quantify like how much amount of knowledge, good knowledge, is stored in this model. And you will see a big jump. That is, there is a factor 20 times difference between the 2 scenarios. So this is not 20%, this is 20 times. So if on the left-hand side, you can memorize, say, maybe 20 million bits of information, of knowledge. On the right-hand side, you can only memorize 1 million bits. So that's a big factor loss. In other words, and similarly, like even if you increase the training time, so say that you make sure the good data got exposed for 300 times, that's 3 times larger than before, still like you have a very large loss, like 3 times loss. So we summarize this as saying that the malexistence of the junk data in the pre-train actually is significantly harm LLM's knowledge capacity on the good data, sometimes by a very big factor. So this is something that we discovered by playing with controlled experiments. So that's pretty sad. At the same time, we also use controlled experiments to discover actually how to fix this. It's very easy. That is, let's consider adding a domain token in front of each piece of pre-trained data. That is, in the past, your pre-trained data looks like concatenating all of the maybe internet pages all together. But now let's prepend each piece of internet data with either the domain name or maybe the URL of that web page. And once you do that, things get greatly fixed. For instance, here, it was 20 times worse, but if you add this domain token, it becomes just 10 times better. And here, like you got 3 times worse, but now you get back the full performance. So in other words, like as long as you add such domain token to the data, then LLMs can automatically detect what are the domains that are rich in high quality knowledge, and then prioritize learning from them. So this is a phenomenon that we discovered by using controlled experiments. So you don't need to teach the model what are the domains that are good. All you need to do is to just put the domain name in front of it. Then the language model is going to automatically learn what are good and what are bad. Okay? So to summarize, in part 3.3, I told you that if the data is sufficiently pre-trained, then pretty much you can hit this 2-bit per parameter of knowledge capacity regardless of the model architecture. And we use that to make some prediction about maybe how large the language model needs to be, maybe in the future, in order to capture all of the human knowledge. And we also studied scaling laws for insufficiently trained models. That is, what if the data is rare? What if the knowledge is rare? In such a case, we see architecture differences. That is, it's maybe better to use the original MLP comparing to the gated MLP. And one thing I didn't cover today is about quantization and MOE. So for instance, we also showed in the paper that if you quantize a model into 8-bit parameters, that is, if you use int 8, you can still achieve this 2-bit per parameter capacity. So this means language models are capable of achieving a compression ratio of knowledge being like 4:1. So that's extremely strong. If you use like zip, I actually tested it last night. It was 100:1 compression ratio. So large language models are super good at compressing knowledge. And finally, I showed you this surprising result regarding how to deal with data of mixed qualities. And the trick is simple, that is to add domain tokens. So that really summarizes part 3. And I want to take a moment to reflect back to this 4 points I have been advocating at the beginning of the talk. So here, in this part 3, I have been focusing only on knowledge. I ignored everything else. I focused only on knowledge. And I designed some synthetic knowledge data. And except for the scaling laws, all of our results are replicable by just using 100 million parameter models. And from there, you can already derive some very universal laws that can apply to much larger models. So by the way, to give you a sense, when you're studying models of this size, if you have a H100 GPU, you can pre-train everything just within a day. But if you don't, like me, I only have V100s. But if you have 8 of them, that's within a day you can do the pre-train. Or even if you just have one V100, then you can still scale down the data because you have synthetic data, you have full control of the data. You can change how much amount of knowledge is there in the data. And even if you scale down the data by a factor of 5, for instance, all of the results are still replicable in today's talk. So we think this is really maybe the way we should go, because once the model is so small, you can really afford doing a lot of controlled experiments. You can tweak the training process. You can tweak the data types to add COT or without COT, or you can tweak the architectures to try to add different things into your architecture and see how they influence the performance of the models. And the final thing I'm saying here is that we used a lot of probing. So all of the statements I made today, both so far as well as the statements I'm going to make in the rest of the talk, are actually supported by probing. That is, we actually looked inside the language models to really discover what exactly is happening. So now let me move to part 2. That's about the reasoning skill of language models. So I'm not going to be able to talk about all levels of reasoning. I'm only going to talk about reasoning on the level of grade school math, that is elementary school math. So this part is a joint work with my intern, Tian Ye, who is a student from CMU, and my colleague Zicheng Xu from Meta, as well as Yuanzhi. So this part is not yet online, but it will be online on archive at the end of this week. So in this part, our goal is to understand the hidden reasoning process of large language models. And in order for us to study this, we propose to actually create synthetic math data set that can simulate GSM-AK. And then we use that data set to understand how large language models think, what is its mental process, what is the reasoning skill that it developed, as well as try to figure out maybe if language models make mistakes, then why do they make mistakes? So this is the goal of part 2.1. And once again, like I'm going to, all of the statements I'm going to say are supported by probing. So to begin with, the goal here, as I said, is to study how large language models solve maybe grade school math problems. But we can't use GSM-AK because the data is too small. We also cannot use GPT-4, for instance, to augment GSM-AK. So one can imagine that you can feed some problems from GSM-AK to let GPT-4 to generate similar problems. You can do this. You can generate even infinitely many of problems in this way. But I claim that in the end of the day, the generated problems may be too biased, and of course, it's only using very few solution templates. So therefore, like, it's not really if you use this approach to generate math data, it's not going to give you a very hard math problems. So for this reason, we really believe it's necessary to develop our own like synthetic math data set. But we also made some assumptions. That is, we try to develop a data set so that you can directly pre-train the language model on such data. So this means that we had better remove the common sense from GSM-AK. So one of the things that's actually very hard from GSM-AK is to know the common sense. For instance, if a candle burns, its length shrinks, not increases. So this is some skill you have to learn from maybe the entire internet data. But it has nothing to do really with the reasoning aspect of language models. So therefore, we decide to remove that. But at the same time, we think it's necessary to keep at least the following things. That is, for instance, the direct dependency between parameters. That is, maybe if a parameter depends on, say, the sum of another two, we want to capture this type of math reasoning things. And we also want to capture maybe instant dependency. For instance, if there are X classrooms and each classroom has, say, Y messenger bags, then we want to be able to understand that in total there are X times Y messenger bags. And also we want to capture maybe implicit dependency. For instance, if Bob has 3 times more fruits than Alice, then X are not fruits. So we want the model to be able to also, we want the data to also be able to capture this kind of parameter dependencies. So let me give you a glimpse about how our data looks like. So here is an easy example. All right. So for each problem statement, it's actually related to 2 graphs. So one is what we call the structure graph. It actually defines what are the possible parameters. For instance, here, this edge captures how many film studios are there in the Riverview High School. So this is a parameter that can be assigned. And for instance, this first sentence of the problem is saying that this parameter depends on 5 times the sum of another 2 parameters. So this is one type of parameter. Another type of parameter that we managed to capture is, for instance, how many bags are there in this high school. So this requires some implicit computation, such as how many film studios are there in this high school and how many bags are there like in each film studio and so on. So that's like a rough sense about what the parameters are. And now each sentence of the problem description captures a dependency description. That is, for instance, here, the River High School's number of film studios, which is this parameter, it depends on 5 times the sum of these 2. So if that's true, then we just we draw a directed graph, from those parameters to this parameter. And eventually, like if you combine all of the problem description sentences, that gives you a DAG, a directed acyclic graph. So this is like how we describe a problem. And now each math problem needs to be followed by a solution, right? So here we use the standard like chain of thought solution to do the computations for this. Let me actually go through this with you so that you can maybe understand a little better how our data looks like. So here, the question is about how many backpacks are there in the central high school, which is captured by this parameter. And we know that it equals to this times this. So therefore, like in your final solution, you have to compute those 2 blue ones before you can compute the final solution. And for instance, for this one, it actually equals to this plus this, and therefore you need to compute these 2 before you can compute the blue one. And similarly for this one, if you look at the problem description, it says it equals to the sum of this and this. So that means these two yellow ones needs to be computed before the green one. And for instance, this yellow one, maybe the problem description says that it's also the sum, I think in this case, of this plus this. Okay, but this time, like, these two are directly specified in the problem. That is, one of them is 17, the other one is 13. So therefore, like, you're done. Basically, in the very end, the problem, the solution is basically a step-by-step computation from the leaves of this topological graph into the final question. And here, like, throughout this part 2, you may notice that I'm going to use modular 23 arithmetics. That is, if it's 7 times 22, I always assume that it's modular 23. The reason is because, once again, we want to focus on reasoning. So if we only focus on reasoning, we had better get rid of other aspects about language models. For instance, arithmetics. I do not want to capture, for instance, multi-digit multiplications. So in this way, if we see a language model, say, fails on this type of task, it's not because of arithmetics, because I'm only using very simple arithmetics. I want to do controlled experiments. I want to make the arithmetics very simple and only make the reasoning part hard. Okay. So that's a very rough description about how our data looks like. There are many subtleties, but there are only 2 things that are important for today's talk. Number 1 is that the sentences in the problem description are randomly shuffled. So therefore, for a model to learn to generate solutions, it's not a line-by-line translation of the problem. It has to figure out what is the first step, what is the second step. It has to do this topological sort. And the other important thing here is that there's this parameter, OP, that captures the number of operations that are needed in the solution. So for instance, here, although the solution has 6 steps, but one of them is a sum of 3 things, so therefore the total number of operations is 7. So this quantity actually captures how hard the reasoning problem is. So you only need to pay attention to these 2 things. And let's now pre-train a language model, for instance, GPT-2, on this data. So in principle, this data is of infinite size, right? But let's restrict it into 2 families of data. In the first family, we call it the medium level of math problems, and we restrict ourselves to problems whose number of solution operations is no more than 15. And in the second case, the hard data set, we focus on the operations that are no more than 21. And we do pre-training on this kinds of data. To give you a sense about how hard a data is if OP equals to 21, so this is an example. So I think it's not extremely hard, but it's at least non-trivial even for human beings to figure out, what is the first thing to compute and so on. So you have to, do some, mental calculation about how to solve this problem. So we even computed how many solution templates are there for each data set. So if you focus on the medium level of problems, then there are at least 7 billion solution templates. And if you look at the hard problems, there are at least 90 trillion solution templates. So therefore, if a language model can learn from this, it cannot be because it's memorizing some templates. It has to really learn the problem solving skills. So indeed, we trained the model and tested it. And what is very interesting here is that we not only tested the model's performance in distribution onto the problems of the same difficulty as the training set, we also tested the models out of distribution math solving capabilities on problems that are actually harder than the training. And we see that language models can indeed out of distribution generalize. So before I even move forward, so this is already a place I can make a claim. That is, language models are indeed capable of learning the skills to solve math problems. And this is not really by memorizing the solution templates. So, there is a debate about, for instance, if GPT-4 can solve some math problems, is it because it's memorizing some solution templates? You can't certify this because you don't have full control of the data. But here, we do have full control of the data. We know that during the training process, the problems are only of this level of difficulty. And during the testing, like you're testing it on totally different problems of longer lengths and so on. And therefore, like we can conclude that language models really have the ability to learn some reasoning skills. But what exactly did they learn? What skills did they develop? So this is actually what I care about in the rest of the talk. So the first thing we discover is that, for instance, the GPT-2 model, by the way, you don't necessarily need to use GPT-2. You can use like Llama or Mistral architectures. But still, like all of them, if you train it on this data, you can recognize immediately that it's developing something that we call a level 1 reasoning skill. Let me explain. So when you're giving like a math problem like this, there are at least 2 different strategies for solving the problem. One is what we call level 0 reasoning skill. That is, maybe you like brute forcefully go over all of the possible parameters that were mentioned in the problem statement and try to just compute them maximally. So maybe if you start from here, maybe this parameter is not computable. Maybe you go to the next one. If it's computable, you compute it. And maybe after go over this like a few number of loops, say maybe 4 to 5 loops, you will be able to maximally compute the values for every single parameters. And in this way, you can, of course, solve the problem and give the correct answer. But a level 1 reasoning skill would be smarter. That is, it would be to do topological sort and then completely ignore the parameters that are not necessary towards answering the final question. And we discovered that it turns out language models can truly learn this level 1 reasoning skill. Okay, so we definitely provided the models with math problems whose solutions are the shortest. But it turns out the models not only can solve the problems, but can also produce almost always the shortest solutions. So if this does not surprise you, let me actually point out why this is like really hard. Because in order for the model to really generate shortest solutions, it has to be able to actually understand what are the necessary parameters before it even starts to generate the first sentence. Right? If the model does not know what are the parameters that are unnecessary, then maybe in the first sentence of the solution it's going to compute that. And if so, then the model is going to generate a solution that's not the shortest. But we discovered that language models actually can achieve this. So this actually necessarily means that the model has already mentally processed itself before it starts to even speak out the first sentence. And this is very non-trivial. So one may think that the idea of using chain of thought is going to break down like the math problems into simple steps. But here I'm saying that even before you decide what is the first step to compute, this requires some mental thinking. And on the next slide, I'm going to use probing to actually convince you that indeed this is what language model did. So remember, like this was how our math problems look like. So the first thing we try to probe is that before the model starts to generate the first sentence of the solution, we try to probe, does the model at this point know if a parameter A is necessary for answering the question? For every possible parameter A, we try to probe this. And also we try to probe in the course of the generation of the solution sentences, say between each consecutive pairs of sentences, does the model know if a parameter A can be computed next? So of course the model knows this parameter can be computed next, but there may be multiple such parameters. Does the model know a full list of them mentally hidden in its internal states? And more interestingly, even before a question is asked, does the model already know what parameter A depends on what parameter B? It turns out, after doing probing, we discovered that the model actually mentally has already computed all of the things here with more than 99% accuracy. So this actually already shows that language models developed a level 1 reasoning skill. Because, for instance, if it mentally knows what are the parameters that are necessary, and if it also knows what are the parameters it can compute it next, then if you take a logic AND between the two, it knows what is the next parameter that is not only necessary, but also it's computable next. And if you follow this logic, you're always going to generate the shortest possible solution. So this is actually how language models achieves a level 1 reasoning skill. But the same thing actually implies something even more surprising here. That is, it actually secretly developed a level 2 reasoning skill. That is, if you look at these like things that we probe, they also hold actually for all the parameters that are not necessary for computing your final answer. In particular, here, even before a question is asked, we discovered that the model already at this point has pre-computed mentally the all-pair dependency graph among all pairs of parameters that were mentioned in the problem statement. So this is a skill that is not really needed for solving the math problems. And it's definitely a skill that humans do not use. For instance, for humans, we really start from the question to reversely identify what are the parameters that are necessary. This is what we do. But I'm telling you that language models actually developed what we call a level 2 reasoning skill by pre-computing all parameter dependencies. So I'm not saying this is like smarter, but this is definitely more amount of things that you compute than the human beings. And we actually view this as a preliminary signal for where this letter G from AGI may actually come from. Because here, the letter G means that language models generalize to skills that are not taught in the training set. It's indeed the case in this setting. That is, the model actually learns to pre-compute the all-pair dependency things among like a set of objects. Once you heard about the dependencies of the objects, even before the problem is asked, the model actually developed this skill secretly. And this skill is actually very crucial for the model to be later fine-tuned for other tasks. Because once it has this ability to figure out the dependency graph, then it can answer like many other things that's different from the math problems here, such as like answering, what parameter depends on what, or maybe the connectivity between things and so on. So it can use this skill to develop basically other capabilities. So we view this actually as preliminary evidence for where this G from AGI may come from. So that's about the internal reasoning skills. That is, we discover how language models actually solve those math problems. And now let's switch the gear to talk about how they make mistakes. So I summarized that language models, at least on our data set, actually make 2 kinds of mistakes. So one is that they occasionally they occasionally compute unnecessary parameters. I'm telling you that they almost never compute, but if you put the problems to be extremely hard, you make the OP to go to as large as possible, then this will eventually occur. So not only like for our GPT-2 that is pre-trained on this data set, it generates like unnecessary parameters. Also, like if you try GPT-4 or 4.0, we actually tried it last month, and on our data set, it also like make this kind of mistakes. That's the first type of mistake. The second type of mistake is that sometimes language models start to compute something by like defining maybe a parameter, but then it gets stuck because the parameter is not actually ready for computation. So we discovered that these 2 types of mistakes are the most common, actually, at least on the data that we developed. So let's try to understand what exactly is happening that caused the models to make these mistakes. For the first type of mistake, recall that I'm telling you that before the model starts to generate solutions, it actually already mentally pre-computes what are the parameters that are necessary. So as a result, we can actually do a correlation test between those kind of errors and whether or not the model has already wrongly computed this necessary thing as true if the true answer, the true label is actually false. Let me repeat. That is, before the model starts to generate solutions, it already pre-computes the entire set of necessary parameters. Then let's compare that set with the actual set of parameters that it spelled out in the end. And we see like a very high correlation between them. So this actually means that there are some mistakes that can be detected even before the model opens its mouth. right? So before it even starts to generate, there are already some mistakes that by just probing into its mental states, its internal states, you can already discover that this is an error, a mistake that will definitely happen. So this means that some of the, if not all of the math mistakes are actually systematic. It's not really due to the generation procedure. Right? Some of people may think that it's due to the randomness of the generation, maybe the model makes mistakes, but this is telling you no. Some of the mistakes are systematic. The model, even before it starts to generate, before it starts to use any randomness, already its internal states is going to tell you that it's going to make a mistake. And the second type of mistake is regarding it's also like something that you can discover a correlation between the probing and the mistake. That is, you can discover that if the model actually mentally thinks a parameter is ready for compute, but actually it's not, then the model is very likely going to make this mistake. So therefore, we actually discovered that to improve the model's reasoning, it's very crucial to improve its mental capability of computing this connect quantity. So this I'm actually going to cover in part 2.2 regarding how to improve the model's reasoning capability by just improving this part. So therefore, we also did some probing to connect how model make mistakes versus what is the internal state of a language model. So the final thing I want to show you for this part 2.1 is regarding scaling laws. So starting from the original scaling laws of OpenAI, they already said that maybe the only size matters. The network width and the depth, maybe they do not matter. And also in the previous part 3.3, I told you that for knowledge skills, the model size, only the model size matters. As long as you use at least two layers of a transformer, then the depth does not matter. But here I'm going to tell you that for reasoning, depth matters a lot. Okay. So here is the experiment you can do. For instance, you can try a smaller model that is tall and skinny versus a larger model that is shallow and wide. So this model has more number of parameters comparing to this one. But you're going to see that the reasoning accuracy on our data set is actually much, much lower than this tall and skinny model. So the reason behind this, once again, you can use probing to explain, is because of this mental processing, this mental pre-computation. That is, you can, for instance, plot the accuracy of this probing task, the necessary task, with respect to how far away the parameter is from the question. And we discovered that the probing accuracy actually decreases for parameters that are further away from the question. So think about it. If a parameter is, say, of distance 8 from the question you're asking, then in order to know that this parameter is necessary for answering this question, you need to do a lot of reasoning steps, at least 8 steps. And that was actually the cause for the necessity of a transformer to have a deep network in order to compute this out. So, we actually use this probing to explain why more number of layers is going to help the reasoning skills of language models. And here you see that the probing accuracy decreases as the distance increases, but if you make the number of layers to go deeper, then the accuracy goes back to close to 100%. So therefore, we conclude here by saying that the depth of language models actually is necessary for reasoning because of its mental computation. So this cannot be mitigated by using chain of thought, because we have already used chain of thought. Right? One can imagine that maybe one can previously think that maybe by using chain of thought, I can reduce a very complex operations into single computations. This is true, but I'm claiming here that even before the first step of the chain of thought, it's like solving a math problem, right? Even before you decide what to compute first, you have to do some mental thinking, and this thinking requires depth, and it's this thing that requires language models to be deep. So this is this is part 2.1. To conclude here, that is, we created a synthetic math data set to simulate GSM-8K, and we used that to study the model's hidden reasoning process. And we discovered that language models exhibit some level 2 reasoning skill that is beyond humans. And we also use probing to reveal like how they make mistakes. And finally, we connected actually the depth of language models with the reasoning length of a math problem. So this is something that you cannot do if you have a pre-trained language model from the internet. You have to do this controlled experiments in order to discover this kind of connections. So the one thing that I didn't tell you, that's also in the paper, is that you can also try our data set and see like how GPT-4 performs. And you can figure out that GPT, even 4.0, like I think we tested it 2 or 3 weeks ago, it cannot perform reasoning with more than 10 steps. So I think most of you know that if you ask GPT-4 like a very long reasoning task, it's going to fail. And we actually systematically tested it using our data set. And we noticed that it may fail. So this means, actually, in the future, if we ever hope for improving maybe the reasoning performance of large language models, we probably have to develop synthetic math data set in order to improve its capability of reasoning. So this is the point I will also come back to at the end of today's talk, but this is only one way, that is to build synthetic data to improve language models' reasoning. Another way to do this is to let language models learn from the mistakes. Okay, so this is part 2.2. So I'm going to begin with a very interesting discovery, that is language models actually often know that they have made mistakes. Okay, so here's what I mean. Recall that language models make the following type of mistake. That is, it sometimes start to define a parameter, it wants to compute it, but then after defining it, it realizes the parameter is not yet ready for computation. So if you start from here, then error will start to occur. So this is a very typical error that the language models experience. So now suppose we do probing. That is, we try to probe from this position, like this, this word as. We try to probe from here to check that whether or not the model actually knows it has made a mistake. And we discover that very often the model actually indeed knows that it has just made a mistake. In other words, the internal states of the model really exhibit a very regretful behavior. It really wants to go back, but it cannot. Now suppose we give language models this ability to go back. Let's see what will happen. Okay? So there are two things that can come out of this. So number one is that I just told you, if you pre-train a model on correct data, then the model is, in some sense, automatically an error detector. That is, you can do probing or fine-tune it very easily for detecting error. And now suppose you use this error detector to try to assist you in the generation procedure. Namely, like whenever you discover that the model realizes it's making a mistake, then you try to go back. Then let's see like how the accuracy improves. So improves a little bit by 2%. So there are two drawbacks here. So number one is that this actually changes how you generate data, right? You have to maybe keep track of two models. So one is the generation thing, the other one is the error detector. But that's a minor thing. The more like important downside here is that it only gives you 2% of accuracy improvement. So why is that? So this is because you're essentially cheating. Yes, you have detected error, but how did you correct it? You were relying on randomness to correct it, right? You were just going back to the end of the previous sentence and let the model regenerate. So this is, in fact, very similar to beam search. Although like beam search actually gives you 0 improvement here, but this still at least gives you some improvement. But all of this are like cheating. They're not really learning from the mistakes. They're just relying on randomness or some retries to correct errors. So in order to really make a model capable of correcting errors, you have to prepare data that already has mistakes and corrections. So in our synthetic setting, this is what we did. That is, we kept the same math problem. But then when generating the solutions, we allowed the data to include mistakes, and with a probability p to include a mistake at the end of each sentence. So here, each mistake is very simple. It's just a parameter that is not yet ready for computation, and then we put a text back. So this is not backspace. It's just a special token called back. So this means that both during the training and during the inference, the model is still like using autoregressive language modeling. That is, for instance, when the model is trying to learn or maybe generate like this parameter, it actually has access to all of the previous mistakes it has made. And we are preparing this kind of data to let the model learn to how to correct its own mistakes it has made. And if you use this data, actually you can see a very huge accuracy gain. All right, so what's important here is not actually the accuracy gain, it's actually a lot of nice properties that come with this. So number one is that we discovered the higher the P is, actually the better the improvement. So you can actually insert a lot of mistakes. Like for in average, like for half of the sentences, you can include mistakes, and this will actually further improve the model's test time accuracies. And another nice property here is that even if you insert a lot of mistakes in the pre-trained data, it does not mean that the model is going to make mistake during the inference time. So this is because even if like P equals to 0.5, during inference, the model still uses, for instance, temperature zero or maybe beam search to find the most likely next sentence to generate. And even though that during the training, like we insert like random arrows, but those random arrows are still like, each of them is still like having a very small probability to be generated. And the most likely next sentence remains to be the correct next sentence. So if you do the math, then you can figure out that the model is still encouraged to always use the correct sentences in its solutions. So therefore, like, you don't need to worry about a model like learning on this data, but suddenly when it generates, like it starts to generate a lot of like errors. It won't. The third property that we discovered is that you do not need label masking. So in the PyTorch language, label masking means that you put like ignore index to be minus 100, right? So one may think that if I have a math data with arrows, then probably I need to put label masking to prevent the models from learning the mistakes. Maybe I only want the models to learn from the corrections instead of the mistakes. But we're telling you that no, you don't need to do label masking. And that doesn't change the performance by too much. So therefore, the last thing I want to say is that even though the solution in the pre-trained data becomes much, much longer than before, but during the inference time, the model still like uses the level 1 and the level 2 reasoning skills, still like gives the shortest solutions. So I'm ignoring all the details, but the main message here is that this is really a very safe method. It's very safe to include math data with mistakes and corrections. And in fact, the more mistakes, the better. And there's no change to the pre-training procedure and the inference procedure. It's still like auto-regressive. So there are two comments I want to make here. One is how to obtain such data in practice, which will come later. But the second comment I want to make is regarding what is the necessary training process in order for this accuracy gain to be achieved. So here, in this experiment, we did pre-train. That is, we used the math data with mistake and correction. We pre-train on this data. But imagine, what if you do fine-tuning? So suppose you take a model that is pre-trained only on math data that are totally correct. And now you fine-tune it using math data that have mistakes and corrections. And could this model A prime perform well? The answer is no, it doesn't. So here, like once again, whenever I write a number here, actually what's behind this thing is a lot of numbers. We really tried the different parameters and different fine-tuning methods. In all of them, the accuracy improvement is negligible. And in most cases, actually, the accuracy decreases. The reason is really, to summarize, like it's very crucial to add those math data with mistakes to the pre-train stage. It's too late to add it at the fine-tune stage. So the reason for this to happen is because, unlike error detections, which are very easy, you can use probing or like fine-tuning to turn a model into an error detector. Error correction is a much, much harder skill, because you need to figure out, what is the mistake you have made and what's the new step you're going to try. So this is a much, much harder skill that you must learn from the pre-train stage. In other words, like if you take, for instance, the Llama like 70 billion model and some existing pre-trained model that's supposedly like not really trained on math data with errors and corrections, then suppose you want to fine-tune it, you probably don't get good results. So this is what our controlled experiments predict. So the last thing I want to show you is how to prepare this kind of data. In our synthetic setting, it's easy to generate this data because you have the full access to the data. You know what's the graph, what's the dependency graph. You can do all sorts of things you like. But in practice, how to do this? In the paper, we actually tried two practical ideas, a dumber idea and a smarter idea. So let me show you the dumber idea. That is, let's try to create fake mistakes. Here, a mistake is fake if it's just a random sentence that appears in the future of the solution. Okay, so let's try to, so for instance, if I'm here, I want to like insert a mistake, then I try to randomly select a future sentence in this math solution and put it here and use this as a mistake data. So of course, like some of the future sentences are not truly mistakes because maybe like they can already be computed here, but still like you can use this kind of idea to prepare a data very cheaply, like, because whenever you have like a math solutions, you can always like divide it into sentences and try to insert like future sentences into previous sentences to make it a fake mistake. And on our synthetic data, we tried this idea, and it actually gives you a very like significant accuracy increase. So it's not as good as the perfect math data with mistakes, but it gives you like some very decent accuracy gain. So this is what our controlled experiments predict. And the smarter idea is actually to maybe try to create a mistake by selecting a random parameter from the problem statement. You can also create fake mistakes like that, but I'm happy to tell you that this doesn't work. So it's actually harder to obtain in practice, and it gives you like weaker results. So therefore, it's actually better to go for the dumber idea. That's actually very cheap to obtain in practice, and you can still hope for getting reasoning improvements. Yeah, we actually give a slogan to this, tentatively, called "Pretrain with fake mistakes, no more regret." So to summarize, this is part 2.2. That is, I first told you like language models often know that they have made mistakes. They really exhibit a regretful behavior, that is, they really want to correct themselves. But they couldn't because they do not have this capability. So in order for the model to have this capability, you have to add pre-trained data with mistakes and corrections to really teach it to do this. And this is a capability that cannot be achieved if you use beam search or fine-tuning. You really have to insert such data on the pre-train level. And finally, like, yeah, you can actually create this type of mistakes, but fake mistakes, very easily, and at least on our synthetic data, we predict that this will give you some quite decent accuracy gain. So once again, let me take a moment to reflect back to this main theme like I'm talking about in this tutorial. That is, in this part 2, I focused solely on the reasoning aspect of language models, and we designed synthetic grade school math level data sets. And we once again used only models of 100 million size parameters. You don't need to go that large because you're just focusing on a specific skill, and you're using like perfect math data, so you don't need the model to be super big. But still, like in this setting, you can tweak things. You can tweak, for instance, the data difficulties, the types of mistakes, or you can tweak the training process to see like how they influence the model's reasoning skills in the end. And also, like we did a lot of probing. We use probing to explain how models reason and how models make mistakes. And even like we can look at parameters at different levels of difficulties, and then to use that to connect the model depth and the model length. So this is a little reflection to like the main theme I'm talking about today. So in the next like 25 minutes, I'm going to talk about part 1. That is about language models learning language structures. So in this part, there are 2 goals. Goal number 1 is to do some interpretations of LLMs that are beyond the token levels. So we have very good language model interpretations, but most of them, like the induction head, is really on the token level. That says, like, if you have AB, later you see A, then the next token should be B. So this is something that's very good interpretation, but it's too easy. And we probably want to do some interpretation of some very hard algorithms and supposedly some hierarchical algorithms. And we also want to give precise interpretations of how language models learn such algorithm. And we especially want to go beyond topological sort, which is still like considered maybe an easy algorithm to most of the audience here. So that's one goal. That is, we want to give some good and precise interpretation of how language models achieve some non-trivial algorithm. The second goal is for us to understand how language models learn structures. So there was actually one thing I kept hiding in this talk. I'm not sure if any of you noticed, is that I never told you like how language models learn formats. Right? So in part 3, I talked about how it learns like knowledge. In part 2, I talked about how it learns like reasoning. But then how about the formats? Like why does it always like use the same format? So in fact, there's a term for this that's called hallucination. So people say hallucination all the time, but to me, hallucination is nothing but the fact that models learn formats faster than the underlying task. Right? If you learn the format very fast, then of course you're going to use the correct format to answer things like you can answer yes and no, for instance, to a parity test. But it just so happened that you did not learn the underlying task yet. So in other words, like language models can learn formats very easily. And to this extent, then let's try to elevate the task to make it harder. That is, let's try to create some hierarchical, more complex language structures to really push the limit of language models to see like how it can solve some very hard language structures. So in order to cover these two goals, we actually found a way to cover both of them. That is to study how language models learn context-free grammars, or CFGs. In particular, we designed our own synthetic CFGs that are very, very hard. For instance, we developed like 20 plus like number of CFGs, and in each CFG, let me remind all of you like how you generate from a CFG. That is, you start from a root, then you follow like one of the rules, say that each of them with a uniform probability of being chosen, and then on the next level, you continue the generation and so on. So in the end of the day, you reach the leaves, and you put down all the characters in the leaves. So that forms a sentence that is generated from this CFG tree. So in this synthetic data, we intentionally made the leaves, made the vocabulary size to be small so that the sentences are always like 1, 2, 3, 3, 2, 1s. So this made the task very, very hard because if you locally look at just the consecutive, maybe say 10 of the tokens, you cannot really identify, what are their parents, what are their grandparents, and so on. So although the CFG has the letter grammar in it, but I want to make a distinction here. That is, CFGs, if you generate it in this way, for instance, is much, much harder than, for instance, English grammar. Because for English grammar, you can pretty much just parse it using greedy. For instance, if you have an adjective followed by a noun, you know that they should be combined together. But in this synthetic CFG that we generated, if you look at some locally, you look at some consecutive numbers, consecutive tokens, it requires you to do dynamic programming to really do the full parsing to figure out, how to segment things and what are their parents. So you can even count like the number of samples you can generate from this CFG tree. This CFG tree is 10 to the 80. So it's impossible for a language model to actually memorize this. So let's now really see, like, if you pre-train a language model, say GPT, on this data, what will happen? So we measured accuracy in 3 different aspects. Number one is that we provide, so after pre-training, we provide the model with a valid prefix that definitely it has not seen in the training because there are too many possible training samples. Then we let the model continue to see if it can accurately generate a sentence that could have like hundreds of tokens that is precisely inside this CFG. And it turns out if you use like relative attention or the rotary attention-based GPT, the accuracy is pretty high. But if you use the vanilla GPT, that is the absolute positional-based, embedding-based GPT, the accuracy is much lower. We also looked from other perspectives like the diversity and the distribution difference. We even measured some KR divergence, and they give you similar results. That is, it's absolutely needed to use relative attention or rotary attention in order to train on this CFG data. So on the next slide, I'm going to tell you actually how, once again, like how GPTs can achieve this I'm going to tell you that. But before I do that, let me already make a conclusion here. That is, just by staring at the accuracies between those two, those like 3 different models, we already see like a very strong connections between rotary embedding and the relative attention versus the absolute positional embedding. Namely, like rotary embedding is really what people use in practice, like in Llama, Mistral, and in many of the state-of-the-art models. But why exactly do we use that? So by playing with this synthetic CFG data, we discovered that actually for learning structures, language structures, it's very, very beneficial to have the attentions to be based on their relative distance. So that was actually at the heart of, for instance, relative attention and the rotary attention. So we know this. But in fact, a very surprising thing is that if you do a controlled experiment, by implementing an architecture that we call it GPT stupid, that does uniform attention, then the performance is also good. So let me define this. In this GPT stupid, I still have multiple heads. In the first head, I always look back to the previous token. In the second head, I always look back to the previous 3 tokens with a uniform weight, like 1/3. And in the third head, I always look back to 7 tokens. In the fourth head, I always look back to 15 tokens. Okay, so exponentially growing, but all uniform attentions. But this GPT already performs much, much better than the vanilla GPT with positional embedding. So this actually gives us a lesson, because if ever in the future we want to get rid of attentions, people are doing this like Mamba, right? We had better still maybe keep track of a uniform version of the attention, which is actually very cheap to implement. But it's actually very powerful for you to, and it enables you to learn some language structures that could be very useful for certain tasks. So I'm not going into the details here, but the conclusion here is that even doing this GPT stupid, it can perform much better than the vanilla GPT. And some other conclusions here include that you can see that relative attention is actually better than rotary embedding. This perhaps very few people know because we don't use this anymore, but the reason is because it only gives you maybe 1% of accuracy gain, but it makes the running time actually slower. So this is why maybe people prefer like rotary embedding, but you have to know that actually relative attention performs better. So this is actually a fact. So now let's really go to the interesting part to discover really how language models learn this and why and how they learn this. So let's recap. So a language model trained on this CFG data is just seeing like sentences like this. It just sees like data like 1, 2, 3, 3 to 1, so very like ambiguous. What's behind the scene is that there was also a CFG tree that generated the whole sequence, but the model does not see the CFG tree. So let's now try to discover that after pre-training, does the model actually secretly learn to parse the CFG trees? That is, if you look at the hidden embeddings, say, of the transformer of the last layer, does the hidden embedding actually encode what is the parsing tree behind the sequence? So the short answer is yes. Not only it encodes this, but it encodes this in the right place about the right knowledge. So for instance, in this, the knowledge about the red boxes, that is, the node for this subtree is called 11, and the node for this one is called 7. So those 2 node names are actually up to a linear transformation locally stored in the hidden states of around this position. And the information about the parent and the grandparent and the great-grandparent are also locally stored here. So everything like in the red box are stored actually very locally inside the blue boxes. It's, of course, like for things in the future, that is, because it's language modeling, right? It's a unidirectional decoder model. So up to, for instance, a point here, the model does not see the inputs in the future. So therefore, you cannot hope for the model to know what are the grand-grandparent of this node or the grand-grandparent of this node. So those informations are not stored here. But I'm saying that for all the information that it can information theoretically be able to parse, it's already stored like in the hidden states of the model. So to summarize, that is GPT not only like can learn the data generated from the synthetic CFG data, but in fact, it also secretly learns the CFG trees. The precise statement is the following. That is, the information about each subtree, that is, say, the root is actually called 13. This information is actually linearly encoded just around the ending position of that subtree, like very accurately. So you may think that this is natural, right? Maybe like all the language models can do this parsing, but I can tell you that BERT does not, or DBERT, any encoder-based models, they do not. So the reason is because encoder-based models are using masked language modeling. So masked language modeling is about maybe say randomly masking 15% of the tokens. And for this task of MLM, it's actually very easy for the model to locally decide what are the missing things by maybe only looking at the surrounding, say, 10 or 20 tokens. The model can already decide, what are the missing tokens. But language modeling is different. For instance, for a language model to figure out what is the next token here, it has to be able to parse actually all the way to the root in order for it to decide what is the next token it can generate. So therefore, like, language modeling is actually a much harder task comparing to masked language modeling. So this may actually explain why, like in real life, we do a lot of decoder-based models. Maybe you can do encoder-decoder, but you should probably never do encoder-only models. So this also relates to part 3, in which I talked about knowledge, where I said if you use bidirectional models, then the models cannot extract knowledge. So that was the part I ignored, but actually the reason is for similar reasons. So now we know that GPTs can learn the hidden CFGs, but how does it exactly achieve this? We actually did some further investigation. That is, for humans, like how do we parse, right? We use dynamic programming. That is, you can define an array such as dpija to represent whether or not some symbol A can generate a subsequence starting from I to J. Or like pictorially, for human beings, the way for us to certify maybe 18 can generate this black box. So in order to certify this, we need to first certify that 13 can generate this sequence and the 15 can generate this sequence. And for instance, to certify this one, you need to first certify these two. So this is called dynamic programming that most of you definitely know. And what I showed you actually 2 slides ago was that, in fact, this DP, this dynamic programming states, were actually locally stored in the hidden states of the language model. And not only that, if you think about it, dynamic programming also has transition functions, right? In order for you to combine these 2 information into like a bigger state, that is, the whole thing can be generated by node 18, for instance, you need to be able to do some connections between the DP states, that is the so-called DP transition functions. And we actually identified that if you look at the attention pattern of the language models, they actually the attentions precisely serve for this purpose of connecting the DP states. That almost completely just simulates how dynamic programming happens here in terms of CFG parsing. So we actually made this very precise in the paper, but this is only 1/2 of the problem, because in order for a language model to learn CFGs, it not only needs to learn how to parse it, it also needs to learn how to generate from CFG. So this actually requires another level of dynamic programming that probably many of you did not know. That is, I need to be able to actually say, like, if I have this prefix, then what is the next token I can generate? Or if I have multiple tokens I can generate, then what are their marginal probabilities? So in order to compute this, you need actually another level of dynamic programming. So this is represented, once again, by some DP states, which are typically written like this, that captures, for instance, if I have this prefix, then can this prefix be followed by some node, say called number 9. Okay, and in order to certify this, you again need to do dynamic programming. So I'm hand waving here, but maybe you can get the point. That is, in order to figure out this can be followed by node 9, I need to first certify that this shorter prefix can be followed by node 10, as well as this node 8 can generate this short sequence, and I need to use the combination of these two information to certify that this prefix can be followed by node 9 and so on. So there is this like another like very non-trivial dynamic programming in which it also has that DP states and DP transition functions, and we also certified that those types of transition functions showed up in the attention mechanism of the transformer after pretraining. So therefore, like transformers are really doing like very smart things. To really summarize on this part one, that as I showed you that GPTs can really learn like very long and synthetic CFGs, and this actually requires some very non-trivial planning, and it requires some very non-trivial like mental computations, which is actually a dynamic programming. This is much harder than topological sort. And in particular, we used probing to actually show that the DP states are encoded in the hidden state of the mechanism, and the DP transition functions are encoded in the attention mechanisms. So this is actually a very strong statement regarding like how, regarding the interpretations of language models. And also like BERT does not. You really have to use language modeling. And one result that I'm skipping today is regarding how GPTs can learn like implicit or corrupted CFGs. It's in the paper, in which like there's also some lesson to be learned there. So I want to actually point out that this algorithm, this two-step dynamic programming, is really very non-trivial. So I asked around, like for among all of my software engineering friends, they didn't know this DP. And among all the people I have interviewed or mock interviewed, none of them actually solved this problem. So the first time I learned about this DP was actually in 2005. That was in IOI International Olympiad of Informatics, 2005. I knew it because I was a participant over there. So this problem actually, a variant of this problem showed up on the second day on the last problem. And I did not solve it. So to this extent, I think even GPT-2 has surpassed the intelligence of myself at the age of 17 years old. So that was actually the thing that really surprised me and drove me into this whole field of studying like, the physics of language models. And in fact, I'm not surprised that GPT-4 can achieve like very fancy things, because it has definitely seen all of the dynamic programming textbooks. It knows what dynamic programming is. But here I'm talking about GPT-2. It did not see what is dynamic programming. All it sees are just those like 1, 2, 3, 3, 2, 1s, those patterns. And they actually automatically learns what is the best algorithm to parse such data, and what's the best algorithm to generate from such data. So that was actually the thing that really interested me to join this study. So in the end of the day, I just want to mention one final thing that is in my mind. I really think this is some sort of future science, because we're using synthetic data. So a year ago, if you tell your friend that you are doing synthetic data in machine learning, like they're going to laugh at you and walk away, and the reviewers will reject your paper. But not anymore, because people are saying that we have run out of real life data. So therefore, like even though that, for instance, GPT-4o probably has already been trained like on all the internet data, it still cannot perform reasoning for more than 10 steps. So therefore, for us to really go beyond this barrier, we have to think about how to propel synthetic data for us to train maybe, if not GPT-5, but at least GPT-6. We have to be prepared for that. But how to study like what is the right format of the data that can enable this? For instance, when we are talking about knowledge, what's the right format of knowledge that we need to give in order for the model to acquire the most amount of knowledge? Or what is the format of the reasoning problems that we need to feed into the training procedure to make the model to be able to reason as long as possible? Those are the things we need to really think in order to build a language model that can move us closer to AGI. So I will just stop here, and it's really my great honor to speak here. Thank you so much.
Thank you, Zerian, for this wonderful and very insightful tutorial. So if you have any questions, you can line up behind the microphones over there. You can go to the microphones.